Okay, welcome to lesson 29 on the fundamental theorem of calculus. Now this lesson's got two parts to it. So this is the first part where we're going to look at the derivative of the area function, and then in the next lesson we will look at when you take the integral of the derivative function of what happens there. So for this one, we're going to look at how this works, and we'll do a little mini investigation just like we do a lot of the times. And what I would like for you to do is on this first page, just draw a random function on the graph below. I've drawn mine in that looks a bit like this. And to get an idea of how an area function works, essentially the lower value of the lower limit is the starting point. So that could be about there. And the x on the top is anywhere to the right of a, and it could be as early as -5, it could be anywhere. So as we're filling it in from left to right, imagine it's filling up with water or sand. I'm trying to shade it in from left to right. This is how the area function is being calculated. So we're working out the definite integrals here as we're moving from left to right, and we could keep going. X could be still over here, it could be underneath here, or it could be continuing on, or it could be, might stop there. So x could be anywhere along the horizontal axis. So we could say x could be there, but x could also be at -5, it could be at 0, it could be anywhere. So the trapped integral of the yellow section would be from a, in this instance a would be -7, to x, where in this instance x is 4, but this is what the trapped area, the yellow section, would be. That's what that area function would be. Okay, so define an area function. We've done that. Shade on the graph. Yeah, I've done that. Shade in a small green strip to the right of x with a width of delta x. Okay, so let's try and do this green. So we'll change this color to green. So we need a small strip. So maybe we'll do a strip from from 4 to 5 in this section here. And really what we're interested in is the width of this green strip. We're going to call delta x. So delta x, and we're really going to call it, actually, we're going to call it h. Let's change it to h. So I'll do that again. So so we'll call this bit h. It makes a bit more sense if we call it h later on. And so therefore, this new value, where the x equals 5 in, if the width of our green strip is h, so the width of our little small section there is h, it means that at 5, where that current dot, that would be x plus h. And so on the y-axis, at where x is, at that point, that'll be where f of x is. And up there, where the 5 is on the y-axis, that will be where f of x plus h would be. Okay, so what we're interested in is we're going to approximate the area of the green strip as the width goes from delta x, we're going to change that to h, as h changes or gets closer and closer to 0. So we're going to look at this area of the green strip as h gets closer and closer to 0. In other words, as h gets really, really thin, what's happening to the area of the green strip. Okay. So to work this out, we're going to use the idea of underestimates and overestimates, and we're going to use like a rectangular approach, so the area of rectangles. So if I was to draw in a lower underestimate of the green strip, it would be that rectangle in there. And if I was to draw in an upper estimate, it would be that area up there. So like a right endpoint estimate, and the lower estimate is the left endpoint estimate. And the trapped area, the bit in green, is going to be in between those two rectangle areas, isn't it? So the underestimate is going to be less than the actual area of the green strip. So I'll highlight that green, that's what we're interested in. And that actual area is going to be less than the overestimate of the area of the rectangle that we've got. Okay, so we've set up our inequality. Now, if we were to calculate the area of the underestimate rectangle, well, the height of that rectangle is going to be f of x, and the width of my rectangle is going to be h. So the area of the underestimate would be f of x times by h. And the actual area, well, if we were to use work it out using area functions, the way we would work it out is on the right-hand side where the x plus h is, that would be the area function of x plus h. And if we subtract the area function of ax, we're going to get left with the green shaded region. So think of like composite areas, composite shapes. The area, if we work out the area function all the way up to 5, or x plus h, and we subtract the area function to x, we will get left with the area of the trapped green section. So that's that bit there. So we'll write a of x plus h minus a of x. And all of that is going to be less than the area of the overestimate rectangle. And the overestimate rectangle has a height of f of x plus h. From there to there is f of x plus h. And a width of h. So we're going to say f of x plus h times by a width of h. So now we've set up our inequalities. We can do some algebra here. So if we divide everything by h, we'll end up getting, well, this first bit, f of x times by h. If we divide that by h, we'll just get f of x. And that would be less than this bit if we divide all of this by h, which would be less than f of x plus h if we divide that by h. Okay, so now what we've got is something that you should have seen from doing first principles before. This bit here is very much what you see when you're doing the rise over run first principles. So what we've actually got, as h tends to 0, as the limit of h tends to 0, well, the actual area of the green strip, this bit in the middle, as h tends to 0, looks like this. So the limit as h tends to 0 of a of x plus h minus a of x over h, all of that, well, from our first principles, whenever we've seen something like that, that's essentially rise over run, isn't it? So that's going to be equal to the derivative of the area function at x. That's what that means. So as as the width of that rectangle gets closer and closer to 0, the area of the green strip, gets closer. Well, what we're saying is because the area of the green strip is going to be between f of x and f of x plus h, but as h gets closer and closer to 0, the area of the green strip is going to get closer and closer to f of x based on these inequality. So as h tends to 0, the area of the green strip gets closer to f of x. So let's have a look at the graph up here, and that kind of makes sense as well. Like if we think about it, as h gets closer to 0, the area of the green strip will approach the height of f of x. That red section there is going to get closer and closer to the height of f of x, that lower left-hand rectangle estimate. So I've written here, it's the height of the function at x. So the height of the function at x. So what does that actually mean? It means that as the limit as h tends to 0, it means that the derivative function is equal to the height of the function at x. So the rate of change of the area function so the area function bit of x let's read that bit. The rate of change of the area function at x, sorry if I'll read my own writing, at x to the y value at x. So that means all we need to do when we're doing these type of questions is just essentially replace the t variable in our equation with x in it. That's just going to tell us the height. Okay, so let's test it out with these examples. Remember, a can be any number, whatever you want, but what we would like is the constant term to be at the bottom, the lower limit. We don't want it at the top. If it's at the top, we're going to have to switch it around. We'll see that in example number 2. So all we're going to do is, for this first one, we've got the derivative of our area function, and we've just found out that the derivative of the area function is just the same as the height of the graph at t equals x, at the horizontal point at x. So all we need to do is substitute where the t is in our equation with x. So this first one is just going to be, instead of 3t, it's going to be 3x minus x squared. We don't need the plus c. Don't need plus c because it's a definite integral still, and when we're differentiating, the constant will go away. So that's why we don't need the plus c. So this next one's a bit different in that we've got this time the x is at the bottom and the constant bit's at the top. So we're going to use one of our integral properties to switch them around. So we're going to flip the bounds. So that means if we do that, the integral will become negative. So I'm going to put a negative out the front, and we'll have d dx. And this time we've got the 3 at the bottom and the x at the top. And 1 minus u over 1 plus u du. So we don't do anything to the equation. This stays the same. We're just flipping the bounds. So that means we've got the negative out the front. And now we're going to do is substitute the x for where the u is. So we've got 1 minus x over 1 plus x. And if we just expand out the negative from out the front, negative 1 and negative x, we'll have x minus 1 on the top and 1 plus x on the bottom, or x plus 1 on the bottom. And then we're done. So whenever you have the constant term at the top of the limit of the bound, so we're going to flip it and make it a negative integral. And then finally, this one's a bit different because on the top it's not just a single x anymore. We can't just substitute x into the function. We've got to substitute square root x into where the t is. But because it's no longer just a linear term or just a straightforward x, we've actually got to be careful and use the chain rule here as well. So remembering that when we differentiate something like that, it's the same as the derivative of x to the power of a half. So we're going to need to know the derivative of the upper limit because we're going to have to multiply our final value by this derivative. So when we take the derivative of the square root of x, we have a half x to the power negative a half, or 1 over 2 root x. So now this is how we do this type of derivative of the area function when the upper limit is not a straightforward x value. So we still sub in the square root of x, so we go e. So when the t is, we replace it with square root x, but we're going to square all of that for the top. And on the bottom is 3 times the square root of x, like that. But the chain rule says we need to now multiply by the derivative of that top function. So normally, for these ones, the derivative of what's in the top function is just going to be 1, right? So you go in that times by 1, so you don't have to worry about it. But this one, the derivative of the square root of x, well, that's 1 over 2 root x. We just did it over here. So now we can tidy it up a little bit. So on the top is going to be, well, the square root of x squared is just going to be e to the x. And on the bottom, square root of x times square root of x is just x, and 3 times 2 is 6, so 6x is the final answer for that one. So those ones are a little bit trickier because you have to use the chain rule. So the general rule for these type of ones looks like this. If you've got the derivative of an area function, and remember the bottom value is any constant, and if the top bound is a function like square root of x or anything more complicated, and we've got some kind of a rule in terms of t, then when we get the final answer, all we do is we replace the t in our function with the function, so it'd be g of f of x, like that, like a composite function, and then we have to multiply by the derivative of the upper limit. So we need to multiply by the derivative of that. Okay, plenty of practice here. If you wanted to pause the video and give these questions a try, the ones I've put on the solutions are A, B, C, F, H, K, and L. A lot of these ones are relatively straightforward. But yeah, give them a try and then check on OneNote for my solutions. I won't go through each of the questions right now. And the ones on the back page, ones I would like for you to do are A, B, and E. Again, check OneNote for the solutions in the content library. And then finally, for this dominoes, again, OneNote will have the solutions to it, but the way it works is with dominoes, you want to be able to come up with pairs of dominoes that are joined together, so pairs of numbers that are joined together, and there's only one possible solution here that works. So draw along the dashed lines to divide the grid into a complete set of dominoes. Dominoes may not overlap. So in other words, you can't have like a pair of dominoes like this and then like that. Like that's overlapping. Can't do that. But essentially, what you need to do is look through the list and you say, okay, is there any 0 zeros that are next to each other? So the first one you're checking is 0, 0. And if you've got multiple ones, like here we've got a 0, 0 there and a 0, 0 there, we don't know which one is exactly the one we need. So we can't be for sure about that one just yet. One of them is right, the other one is wrong. So we go to the next one. We check 0 and 1, looking for zeros and ones. We've got a 0 and 1 there and a 0 and 1 there. Again, we've got multiples, so we're not sure about that one. So skip that one, go to the next one. So I'm just putting a dots in here to check what I've got, what I'm up to. 2 and 0. There's a 2 and a 0 there and a 2 and 0 over there, so it can't be either of those two. Hopefully we can get one relatively quickly. 3, 0. Here's the next one. Oh, it could be that one or that one. Still not sure yet. 4, 0. Oh, this could be it. This could be our first one. You've probably seen it already. I'm still looking. Okay, there it is over here. So I can't see any other 4 zeros. So that one there is a lock. So that 0, 4 is the only combination we want. So that's what we need to do, is basically go through the entire grid, and at the end you'll have these pairs of numbers. And there's only one solution. Again, check the answer on OneNote when you're done. All right, that's the end of the lesson. We'll see you in the next one.